Hello, I would like to welcome you to lecture 18 of 3N03. We'll continue our discussion in this lecture of amplifiers, single transistor amplifiers, and in specific we'll discuss the common drain amplifiers, common gate amplifiers, and the Cascode D amplifier. This will be the main parts that I plan to cover in this lecture. This lecture is taken from the book of Floyd, chapter 9, pages 460 to 471. We discussed in the previous lecture the common source amplifiers, and we have seen that similar to this shown figure here, we have the source either it is grounded or is connected to a resistance that is being shorted by a parallel capacitor. And this means in the AC analysis or in the small signal analysis, the AC signal is applied between the gate and the source, while the output is taken between the drain and the source. So the source is common to both the input and the output. The same thing can apply as well for the case, it can be applied using not only enhancement type MOSFET but a depletion type MOSFET. In a depletion type MOSFET, if you recall, we agreed that this transistor is naturally on. So if you apply VGS equal to 0 as shown here, you still have a current flowing from the drain to the source. IDS will not be equal to 0. Actually, for this one, the threshold or the off voltage is negative. So as long as you have some VGS which is negative but is above or greater than the VGS off, there's still some current flowing in this transistor. The great thing about this transistor is that we don't need to do special biasing for the gate. We can simply connect the gate to ground through a resistor. And what's happening here is that because there is no current flowing into the gate, what you get is that the effectively VGS for the DC analysis is equal to 0. Of course, for AC analysis, not 0, because in AC analysis, this capacitor will be short circuit and the AC signal is connected directly to the gate. So in that case, for the AC analysis, the gate is not short circuited to ground. So for this one, the good thing about it, as I said, we can simply connect the gate to ground like in this case. In that case, VGS, the DC VGS is equal to 0 because there is no current flowing into the gate, no DC current flowing into the gate, and in that case, our operating point is here. So if this is our operating point, of course, the slope of this operating point will determine the ratio of delta ID to delta VG, and then, of course, as shown in this figure, and as discussed earlier, this determines the gain that we get from such an amplifier. Okay, let's take a look at an example here. We have an example with a depletion type MOSFET. It's a depletion type MOSFET because you can see this line here is not a broken line, it's a solid line, indicating that this transistor is naturally on when VGS is equal to 0. And here we have a load resistor of 3 kilo ohm, we have a drain resistor of 6 kilo ohm, we have a resistance from the gate to ground 150 kilo ohm, we have 10K, but effectively with the presence of this capacitor, this 10K does not participate in the DC analysis, it only applies in the AC analysis. So we know for this MOSFET that IDSS, this is its depletion type MOSFET, IDSS is 1 milliampere and VGS off is equal to minus 2 volts. And if you recall, I mentioned in a previous lecture that for depletion type MOSFETs, we use the same notation we use for JFETs. So we talk about IDSS, we talk about VGS off. We would like to determine the gain of this amplifier stage. And as I said earlier, what you have to do, you have first to determine the DC bias points, DC bias point. So you have to determine the voltage and currents everywhere in the circuit when there is no AC, and when we are handling the DC part, this capacitor is open circuit, this capacitor is open circuit. So we are disconnected from the load resistor, we are disconnected from the AC source. We can find the current flowing in this circuit, we can find IDS, we can find VGS, and this will give us the point on the saturation curve so we can determine the GM. Once we have determined GM, we go back and then we do another AC analysis. We ground this source, this ground is now, this source here, this 10 volts is grounded. This capacitor will be short circuit, this capacitor will be short circuit, and then we replace the transistor by its small signal AC model. So now let's start by doing these steps. First we do the DC analysis and then try to find the operating point. Okay, so I redrew the circuit after I got rid from the capacitor here at the input and the capacitor at the output. The other resistor is really hanging in air, so it's not part of our DC analysis. So because we don't have any gate voltage, any gate current flowing into the gate, we agreed this is a capacitor. So this means that the gate voltage is equal to 0 because there is no current here, there is no drop across this 150K resistor. This means that VG is equal to 0, but VS is equal to 0 because the source is grounded. Then this means that VGS is equal to 0 as stated here. Okay? Remember always that VGS is equal to VG minus VS. It is 0 minus 0. In some applications it will be 0, some others to be positive, some others will be negative. So you have to determine depending on the circuit. Now I know that VGS is equal to 0. I can now assume saturation, assume that the relationship between the VGS voltage and the current is quadratic. So we assume this relationship here. Of course, the VGS is equal to 0, so this term is 0, so this will give us 1 squared multiplied by IDSS. IDSS is 1 milliampere. This means that the current flowing from the drain through the transistor and to the source, it is the same current. This current is equal to 1 milliampere. So we now know the current. We are all set to determine now the transconductance. Transconductance is by definition the derivative of this equation relative to VGS. So it's the derivative of IDS relative to VGS at the operating point. And if as I mentioned before in the lecture, this slope, this value, if this is a curve, IDS versus VGS, the slope of this line determines the gain of the amplifiers. This is what we call GM. So we have first to determine GM and then we can take it into the gain part. So now we move to determine the value of GM as shown in the next slide. GM by definition it is the derivative of IDS versus VGS. So if you differentiate the quadratic equation you get this expression here. Minus 2 IDS or VGS off multiplied by 1 minus VGS or VGS off. Our operating point has VGS equal to 0, so this term will cancel out. So you end up with minus 2 multiplying 1 milliampere divided by minus 2, because VGS off is equal to minus 2 volts. Minus 2 will cancel with minus 2. This means that GM has a value of 1 milliampere per volt. Now we know what is our small signal model. Our small signal model looks something like this. There is a current source. It has a value GM VGS. It's flowing from the drain to the source. Okay? And then this is our source here. This is a common source configuration. This is the gate. Okay? And this is what we call VGS. So this is a model that we replace the transistor with in order to calculate the gain for small signal AC analysis. So now I go back to the original circuit and I remove the DC source, the source that we have here, the VDD, I ground it. All capacitors are being short circuited, so the capacitor here is short circuit, the capacitor is short circuit. And again, if you have a closed formula that you know for this configuration and you are sure of this configuration, please go ahead and use a closed formula. I prefer to drive it from scratch to show you how to calculate the gain for these sort of amplifiers. So here you can see we have this is a load resistance 3 kilo ohm from the drain to ground. We have this drain resistor now, it's connected from the drain to ground. So these two are in parallel. Their parallel combination, 3 in parallel with 3, 6 in parallel with 3. So it's 6 by 3 over 6 plus 3 will give you 2 kilo ohm. The same thing will happen here. We replace everything connected to the gate by its Thevenin equivalent. We have here 10K in parallel with 150K. This will give you 9.3375 kilo ohm. And because this 150K is way higher than 10K, most of the source voltage will appear across this one here. And if you make your calculation, you will realize that the 93% or 0.937 Vs is the value of the Thevenin voltage looking into this circuit. So this is now the Thevenin equivalent that we will use it to replace everything looking to the left of the gate. And of course, as we agreed, these two are in parallel between the drain and ground, so I replace them by 2 kilo ohm. So now we're all set. We get rid of this transistor. We replace it by its equivalent circuit, a current source, and an open circuit input stage. So this is how the circuit will look like as shown in the next slide. So this is how the circuit looks like after you make your simplification. This is the drain, this is the source, this is the drain, this is ground. Okay, the source is ground here. VGS is the voltage between the gate and the source, which is ground. So this is VGS, and this is my input stage. Of course, because the gate is open circuit, here for the AC source, we don't have really, it sees an open circuit effectively. So 93% of the voltage is what's being drawn to this part. So now we're all set to determine the gain. This is one loop, this is one loop, and the current source flowing into this loop depends on the value of the input voltage. So here this current flows this way, then V out is equal to GM VGS multiplied by 2K with a negative sign. Why with a negative sign? Because as this current flows from here to here, from the negative to positive, it's creating a voltage drop with an opposite polarity, plus and minus. So it is opposite to V out. This is why I have this expression for V out. It's minus GM VGS multiplied by 2K. I replace VGS by its value. The value of VGS is this voltage here, 0.9375 V source, the original source voltage we have. This is 2K, this is fine. Remember, GM is equal to 1 milliampere per volt. When you multiply it by 2K, the K will cancel with the milliampere, then you end up with 2. You end up with 1 here, multiplied by 2, multiplied by 0.93375. You end up with a gain of minus 1.875 of V source. So this is the gain of this stage. It amplifies the signal by 1.875, and this negative sign is simply saying that if we apply a sign, what you get at the output is a negative sign. So if this is our input, this will be the output, will be almost multiplied by 1.875 in amplitude, but there's a phase shift of 180 degrees. Okay, so this is an example of a common source amplifier, but it was implemented using a depletion type MOSFET, a naturally on MOSFET, where the off voltage is a negative voltage. A second type of interesting amplifier we will see very often is a common drain amplifier. And here this one, and there are actually so many other configurations of amplifier, but these are the three basic ones: the common source, common drain, and common gate. And here if you see, the input is applied to the gate, and the source is not grounded. The source is actually connected to a resistance RS. At AC, this RS becomes in parallel with another load resistance RL. So the output is taken from the source. You can see the output here is taken from the source. This is what's connected to the loudspeaker or whatever you have on the other side. The drain is connected directly to VDD, and for the AC analysis, this will be ground. So this is why we say for AC analysis, the signal is applied between the gate and ground, which is VDD, which is the drain, and the output is taken between the source and the ground, which is the drain. So this is why they call this amplifier, it's a common drain amplifier. The input is applied between the gate and the drain, and the output is taken between the source and the drain. This stage, and the book of Floyd does not give a proof of that, this stage has this equivalent gain. GM-RS dash over 1 plus GM-RS dash. What is GM? GM is the transient conductance of this transistor. And by the way, this expression will apply if this is an enhancement type MOSFET or depletion type MOSFET, or it's a JFET. Okay, the same expression will apply. RS dash is the total resistance seen in AC by the source. So in AC, the source sees RS in parallel with the load resistance. So this parallel combination is what we call RS dash. This voltage gain you can see is less than 1, and if this number is big, it will be very close to 1. And of course, because there is no current being drawn from the input, the power gain is actually way higher, because you are not really drawing any current from the AC source, or very little current goes through this high resistance. But effectively, you are not really taking any power from this source, but you are supplying significant power to the load. Okay, so here we have an example, and I thought as a first example to show you how to drive the expression for the gain. The book of Floyd does not give a proof of that, but I think it's very helpful to see how we can analyze other configurations, not only the common source, but the common drain and the common gate. So this is a common drain amplifier. You can see this is the drain is connected to VDD, which becomes a ground in AC analysis. And we would like to find the expression for the gain and the input resistance. Of course, and at AC, the input resistance seen by this source is simply Rn in series with Rg, because there is no current being drawn by the gate. So this is the input resistance. What is the gain? The gain is the ratio between V out, which is given by this polarity here, this plus or minus V out is here, is across the load resistor, to the input voltage here. How can we find that? I'm not interested in doing the DC analysis. I will just show you for the AC circuit how I can derive the expression for the gain. So I will start by shorting all capacitors and make them short circuit. I will make this one ground, and then I will assume that I already determined my bias point, and then I will proceed to do the AC small signal analysis. Okay, so this is how the circuit looks like for the AC small signal analysis. Capacitors have been replaced by short circuit. VDD has been removed, is now ground. So now we can see the input is applied to the gate, so between the gate and ground, but the ground is really VDD. The output is taken from the source and the ground, which is connecting the RL, but ground is VDD. This is why it's a drain. This is why we say that it's called a common drain. It's a common drain amplifier. So we simplify things. We replace RS by RO in parallel with RL by RS dash, because this is the equivalent resistance seen connected between the source and ground. So if any similar problem, you have to find the equivalent resistance. Sometimes you don't put RS, you have only RL, but keep in mind it is whatever is connecting the RS. So I did one more step of simplification, and I replaced everything to the left of the gate by its Thevenin equivalent. So there is R Thevenin and there is V Thevenin. And V Thevenin will be a function of the source voltage. Usually it's very close source voltage, 0.99 or 0.98, depending on the configuration. So this is now how the circuit is being simplified. Very simple now. We go back and replace this circuit by a current source connecting the drain and the source here, and then an open circuit between the gate and the source, and the current flowing between here and here will depend on the voltage between the gate and the source. So now let's do the AC analysis. Get rid of the transistor, replace it by its equivalent AC small signal model. Okay, if you do that, this is what you end up having. It looks a little bit irregular to us, but this is the drain. This is the current source flowing from the drain to the source. This is the source here. This is the resistance connecting the source to ground. And this is our output. We take the output between the source and ground. Okay. Now, this is the gate. This is the resistance connecting the gate. And this is the gate resistor. And VGS, the tricky part here is that VGS is between the gate and the source. So it has to be between here and here. So I can redraw this circuit to make it a little bit simpler, because this is ground and this is ground. So this looks like one loop. Okay. So I redraw it again this way. Okay. This one is exactly equivalent to this one. And this is my output voltage from here to here. But the only difference is now this is now my source. So I moved the source up. Source moved from here. It became here. This is my source. This is the gate. So this is VGS. Now we have to find the gain. This is my output voltage is taken across RS dash. So the output is equal to GM VGS multiplied by RS dash. Here it's non-inverting amplifier, because if you make a small change, if VGS is increasing, then the current flowing here will also increase and the output voltage will increase. It's non-inverting amplifier. It's not like the common source one. The common source was an inverting amplifier. So here I can simply say the output is simply equal GM VGS multiplied by RS dash. The tricky part is to express VGS in terms of the Thevenin voltage. And how do I do that? I get it from this loop on the outside. Take a look at this loop. This loop is saying that V Thevenin, there is no drop across the resistance because this is open circuit. V Thevenin is equal to VGS plus the output voltage, which is equal to GM VGS RS dash. So we have this expression here, and this is the expression that we need, because this expression allows us to get rid of V threshold, which is V Thevenin. I'm sorry, I keep on calling it the threshold. It's V Thevenin, the Thevenin voltage. It allows us to express VGS as a function of the Thevenin voltage. And remember, the Thevenin voltage is a function of the source voltage as well. So if you divide both sides here by this term, you end up with this relationship here. But the output is equal to GM VGS RS dash, the current source flowing into this resistor. I get rid of VGS and replace it by this expression here, and then to get the expression for the gain. So this what I got. I removed VGS and replaced it by, in terms of V Thevenin, and when I do that, I get this expression here, which is exactly what I mentioned in the beginning. And to keep in mind, RS dash is the total resistance connected between the source and the ground. In our case, we had two parallel resistances, one connected to the source and one as a load resistor, and their net combination is what gave me RS dash. This number usually is close to 1. It's usually less than 1. If you make this one big enough, it becomes very close to 1. So this amplifier, this common drain amplifier, gives you a unity gain, a unity voltage gain. But it has a much higher power gain, because as I remember, as I mentioned before, we are not really drawing any current from the source. The source is connected to the gate, and the gate effectively draws very little current, and as a result, the power gain will be pretty high. Okay, let's see one more example on this one here. Consider the shown small signal model. This is one here that's done using an enhancement type MOSFET. This is the source, this is the drain, and I'm showing you here the AC model. I'm not showing you the complete circuit. I'm showing you the case after I made some simplifications, after I removed the DC sources, after I shorted all capacitors. We call this model a small signal AC model. I would like to find for this one the ratio between the output voltage and V Thevenin. I write here V out, but of course I also mean V note. It's the same thing. And I'm giving you already the information that you need from the DC analysis. I'm telling you that the bias point was selected such that GM is equal to 0.491 milliampere per volt, and that the load resistance is equal to 10.7 kilo ohm. We tried before an expression for the common drain amplifier. This is a common drain amplifier. We said that the gain is equal to GM-RS dash over 1 plus GM-RS dash, where RS dash is the resistance connected between the source and ground. So what we call RS dash in our expression is what is really called here RL. Okay, so I don't need really to carry that. If you are confident that this formula applies, and I'm confident to that right now, I'm going to be using this formula directly. I don't have to drive everything from scratch. So the ratio between V out to V threshold is simply equal to GM V RS dash over 1 plus GM RS dash. I know GM, I know RS dash, which is equal to RL in this case, 10.7 kilo ohm. So we do the calculation. If you substitute, this is GM, it is 0.491 milliampere per volt, or 4.91 10 to the minus 4. I know RL is 10.7 kilo ohm. If you make this calculation, you get 0.84. Now, if I know V Thevenin as a function of V source, remember we have an actual AC source, but we replaced everything to the left of the gate by a Thevenin equivalent. If I know the ratio, I multiply V Thevenin by Vs. For most of the problems we'll have, most of the voltage appear, most source voltage appear across the gate. So I put this one here as say 0.99, then the exact expression that you get for the gain is 0.83. In a typical example, either I will give you I'll give you this ratio, or I'll simply ask the gain as V out over V Thevenin. I'm not going to get to the Vs part.